Example 1, it says, what is the sum of f of x equals 3x plus 4 and g of x equals x squared minus 5x plus 2? Now, when it says what is the sum, they're asking you to create a function called f plus g of x. Sometimes the book will just say find f plus g, they won't put the of x part. It means the same thing. So f plus g of x or just f plus g. One or the other, they're going to give it either way, but this is the way I like to write it, but sometimes the book will just say find f plus g. It means the same thing. All right? So I'm not going to put that there. And before we do f plus g of x, I want to discuss domain, what domain is, because there's an implied domain question in this statement. If they're giving you a problem of this variety, they want to know what the domain of these functions is and what the domain of the sum of the functions is. So, let me just define domain for you. Domain is the set of all values of x that can legally be substituted into a function. I don't know if that matches the book's definition word for word, but that's what domain is. It's every value of x that can legally be put into a function that doesn't cause any kind of mathematical issues. Okay. Division by 0 is illegal. Taking the square root or an even root of a negative number is illegal in the real number world. All right? So when we're dealing with domain, we're usually dealing with real numbers. So we don't want to deal with anything that's illegal mathematically. So specifically, the two things that really happen in this class a lot, until we learn a few new functions, is division by 0 is illegal. Do this earlier like this. Can everybody see what that word is?
Illegal.
Even. All right, and I got to write it one more time. Bring it. I can't write it tiny like that, make it look neat. So, even root of a negative number is illegal. So when I'm identifying what a domain is, I'm going to be using those criteria for mathematical reasons for domain to happen. Other places domains happen if x represents the number of sides of a polygon. Well, polygons can only have 3 sides or more. And they can't have 3.7 sides. They have to have 3 or 4 or 5 or 6. So your domain would have to be an integer 3 or bigger. All right. If we're talking about the price of an item, well, the price of an item should be positive. So the price, if x represents the price of an item, that price should be positive. Number of people who are going to buy something, that has to be a positive number also. So the number of people should be greater than or equal to 0. So domain can also have like real world connotation. Even though mathematically this equation we can put any number we want to into, only these numbers make sense because we get results that make sense in the real world. All right, so that's another place domain happens, and that's going to happen today also in example 3, so you'll see that. But this idea of domain is going to be embedded in these problems. So what I want to do on these problems to start off with, and it's going to be written down on this problem, it's going to be mentally looked at in future problems. So what I'm going to write down for the most part is going to be stuff happening inside your head. The domain in your answer needs to be written down. So the domain of this has to be written down. Everything else, I'll say the head stuff will be doing a red color. So I'm going to grab that, make it smaller. Everybody copy all that stuff down so I can shrink it up and get out of the way.
Yeah.
I wonder how small that even's going to get now that I'm going to shrink it up even more. That's way too tiny. Let's go there. All right, now it's out of the way. All right, so the domain of f of x equals the set of all x values such that x is an element of the set of real numbers. That's how we write a domain out. Okay. Now, domain is it's a set builder notation, but it's called set theorists are very, I guess, for lack of a better name, lazy people. They don't want to write a whole bunch of words to describe something. So they instead come up with all these symbols to say all these words. So again, that statement up there, very short, compact statement, says the domain of f of x equals the set of all x values such that x is an element of the set of real numbers. Again, it's very, very wordy, but it's very compact, because our set theorists don't want to write all of those words, get writer's cramp. Now, a lot of people get really freaked out about that whole thing. Let me just point something out. Every domain you get is going to have all this stuff here always the same. The only thing you have to figure out is what's not highlighted there. And the way we do that is we look at illegality. All right? Division by zero is illegal. Square roots of negative numbers are illegal. Even roots of negative numbers is illegal, right? Does anybody see division by x in this problem? Are we dividing by x? No. So division by zero isn't going to happen, right? Anybody see any radicals in that expression? So there won't be any even roots, right? So there's no number in the world that can't be multiplied by 3 or added to 4. So x can be anything it wants to be, which is all real numbers. Using the same idea, the domain of g of x equals. Now, one other thing, these braces are what you're supposed to use. I'm okay with set brackets also if you prefer to do a set bracket. Those of you who are more artistic than I am, you can do little braces and have nice, neat little braces, but set brackets are fine also. Take a look at g of x, which is over here. Highlight g of x in green. Does anybody see division by x in g of x? This over here. This is g of x. Is x being divided? Are there any radicals? No square roots or anything, right? So none of this stuff happens, which means all real numbers again, right? So x is an element of the set of real numbers. And just real quick, the real number set, the abbreviation is this fancy looking R. You put 2 vertical lines. You start from the top back one, make an R to the front one like that. That's how you do it. It's just a fancy R. It means the set of all real numbers. It's just, that's how they write it. Looks fancy. So, all right. So again, that's the domain of both things. And again, for me, if I'm doing this problem, all this stuff is inside my brain. I look at the domain of both functions individually to determine the domain of the sum of the functions. Because that's part of the answer to the domain. All right? So, if I'm working the problem out now with that knowledge inside my brain, f plus g of x simply means to take f of x, which is 3x plus 4, and add to it g of x, which is x squared minus 5x plus 2. That's all f plus g of x means. Add the two functions together, the expressions that those functions are. F of x is this expression, 3x plus 4. G of x is the expression x squared minus 5x plus 2. Add them together using good algebra. So if I simplify this, I like to go in descending order, highest power first. This plus sign is distributing through here. So it's plus x squared, so that's positive x squared, right? That's the only x squared object. I've got 3x plus negative 5x, which equals 3x plus negative 5x. Negative 2x, right? And then positive 4 plus positive 2 is positive 6. Pluses and minuses in front of every term. But again, it's just combining like terms. 1x squared, 3x minus 5x is negative 2x, 4 plus 2 is equal to 6. All right, that's what f plus g of x is. That's part of the answer. The other part is the domain. The domain of f plus g of x equals the set of all x such that what? All right, so domain is the intersection of the domains of the two sets. So it's all the numbers that are the same of both sets. And notice, this is all real numbers, that's all real numbers. So what's the same? This is every number in the world, this is every number in the world. What numbers are the same? All of the numbers, right? So the intersection of the real number sets, they're both the same, is simply x is an element of the set of real numbers. In polynomial world, that happens pretty often. Because polynomials are usually all real numbers, unless you're dealing with a real world example, in which case you have to deal with the real world requirements, right? But if we're just dealing with abstract stuff like this, any number can go in here, any number can go in here, so any number can go in there. So that's domain. So the answer to the question is both the sum of the functions and the domain of that end sum. So your homework should look kind of like what's written in blue here. Again, the stuff in red is probably inside your brain. You establish, well, that's all real numbers, that's all real numbers, what's the intersection of those? All right. Maybe you get a domain that says x is greater than 0, another one says all real numbers. Suppose you get that scenario. So suppose you have one domain as x is greater than or equal to 0, the other one is all real numbers. If we're doing the intersection of those sets, this is every number in the world, this is only numbers greater than or equal to 0, so the intersection of these two sets would be x is greater than or equal to 0. Maybe you get x is greater than 2 and x is less than 8. This is everything bigger than 2, this is everything less than 8. Bigger than 2, less than 8, they're overlapping in here in the middle, right? So the intersection of these two sets would be 2 is less than x is less than 8. Sam, pick a number bigger than 2 that's not less than 8. No, that is less than 8.
That's bigger than 2?
Bigger than 2, less than 8.
5.
5's true, 5's true, right? So 5 makes both of them true. 5 is between 2 and 8, right? If I pick 77 is bigger than 2, right? Well, 77 is not less than 8, so it's not in the intersection, right? So this is describing numbers that do both things. So that's, again, all an intersection is. So the domains of the individual things will be whatever they are. It's your task to establish an intersection. If they just happen to both be real numbers, which they are quite often, it's just all real numbers. All right, so just keep that in mind that we do have to find a domain. You want to find the domain of both, and then figure out the intersection of those domains to get the domain of the sum difference product.